Okay, so I would like to write a projector from R3 to the subspace spanned by these two vectors, right? Projector should act as identity on its image vectors. So projector should send this element to itself, this element to itself. What about this one? Well, it can send it to 0, for example, right? So define P hat from R3 to R3 as P hat of 1 minus 1 0 is just 1 minus 1 0. P hat of 0 1 minus 1 0 is just 0 no 1 0 minus 1 1 0 minus 1, and P hat of the third vector to 0. I can do this. Now we claim that this is the projector we were asked to find, right? So times it 0 0. İşte üçüncü vektörü sıfıra götür. Claim P hat is the is a projector with image. What was image? S. Well, of course, image of P is just S because image vectors. This is in S, right? This is in S. This is in S, and this is in S. This is 0 vector. So these three vectors are mapped into S. Therefore, any vector will be mapped into S because any vector is a linear combination of this. Therefore, its image will be a linear combination of these vectors, but they are all in S. Therefore, so image of you had what we need to show is the following. P hat should be also a projector. So we must show P hat is a projector. Why is that? Well, we have to check what is P composition P. Aslında burada da fazla bir şey yapmama gerek yok. So we must do this, right? This is a linear map. This is also a linear map, right? Composition of two linear maps is a linear map, and this is a linear map. To check that these two linear maps are the same, it is enough to check this on base element because any linear map is uniquely determined by its images on a base. So if I show that these two linear maps agrees on vectors of the basis, then they are the same. So we have this basis already. So just do that. So let's say P1 is this vector, 1 minus 1 0. P3 is 1 0 minus 1, and P3 is 0 1 0, right? Okay. Now let's check whether all these agrees on these vectors. P composition, P hat composition code on E1. Well, this is just P hat of E1. But what is P hat of E1? Well, P hat of E1 is just E1. So this is just E1. And P hat of E1 is again E1. But this is just P hat of E1. So on E1, this and this operators agree. What about E2? If I write here E2, I have E2 here. This will be also E2, E2, E2. So for E2 it also holds, right? Yani bir yerine iki yazıyor. The same average. E2, E2, E2. Because P of E2 is also E2. So we have this. Therefore, this operator and this operators agree on this basis element, this basis element. Now we have to check whether they agree on this basis. If I put E3 here, PE3. What is PE3? Well, that is 0, right? This is the 0 vector. P of 0, image of 0 is just 0. So this is 0. But P hat of P3 is also 0. So this and this agree on the third basis element also. Therefore, they also agree on this element. Hence, these are the same. Yes.
John, how did you determine the last base map to 0? Yeah.
Or how I define this. I mean, I define my projective like this. I'm defining a new map. By the proposition I put last time, we saw the following. If you give me a basis, let's say consisting of n vectors, and any n vectors in the other vector space, then I can write a linear map, taking the first basis element to the first element, second basis element to the second element, and so on. And that defines a unique linear map. So I take this basis element, send it to itself. I can send it anywhere, but since I want a projector, I want it to be identical on the subspace. So I send this element to itself, this element to itself. The last remaining basis element, I send it to 0. So the image is completely in S, and it satisfies the following thing. This map is the same as this map, therefore it's a projector. P'yi? Tamam. Bakalım mümkün. If it is a linear algebra, it is usually possible. So it may take some time. Let's just try. Yes.
Where do we know P0 is 0?
I don't know. I define it that way. I declare it. It is. You mean this one?
No. In there, we write
P3. E3 is this one.
okay, it's 0. Then we wrote that P hat 0 is equal to 0.
Yes.
Where do we know?
This is a linear map. Linear map sends 0 to 0, right?
Where we know it's a linear map.
I mean, P is a projector. It is a unique linear map sending this three vectors to this one to itself, this one to itself, this one to 0. I want it to be linear.
Okay, before defining, you say that P hat is linear map.
In the proposition, where was the proposition? I guess the proposition was the following. If you give me a basis, suppose, so this is the basis, E1 up to En, and some other vector space and elements, arbitrary elements, then there exists a unique linear map. linear map from D to W, sending EI to FI. Let me prove this. It is linear by construction. So I define my linear map here, my linear map, P hat, this way. These are the basic elements. I send this basic element to itself, send this basic element to itself, and send this basic element to 0. I can define it any way I want. That proposition gives me that right. Tamam mı? Sor.
Geri gönderdiği mesela elemanlar mesela sevgili resim mi oluyor? Burada
Sıkıntı olmuyor çünkü bu sıfır. Yok. Any questions? No, sor.
Her subspace bir tane project'ında, her subspace için bir tane project var.
Aha işte onu yapıyorum. Aha.
Infinite olursa
Ya, sıkıntı onlar. Infinite dimension vector space'in basis'i var mı? O da sıkıntı. Var ama hani o işte axiom of choice falan kullanıyor. Kolay değil. Your friend asked the following. Can you write this projector in the usual sense? X, Y, Z is sent to somewhere, right? Kim sormuştu? Onu sen, tamam. Onu sordun değil mi?
Ben direkt bir tanım olabilir miyiz? Böyle
Direkt,
X serisi ABC olarak çıkaran ve bunlar da sağlayan.
tamam. Bulabiliriz ama dikkatli olmak lazım. So, write X, Y, Z. First, you want to write this in basis elements. What are the basis elements? 1 minus 1, 0. 1, 0, minus 1, 0, 1, 0. Peki, sadece birinde bir olan var mıydı? Bekle yok. Şurada sadece şey var değil mi? Başkası yok. O zaman burası Z. Minus Z. Bunu yaptık. Şimdi neye bakalım? Şuna bakalım. I want X here. I have minus Z here. So X plus Z here. Right? X plus Z minus Z is X. And here Y'ye baksak
Y minus X minus
ne dedi?
Y minus X minus Z. Plus X.
Plus mı? Z. Bakalım. X artı Z. X var. Tamam. Gitti. Tamam. Now, what is P hat then? X, Y, Z. P hat of this. Right? P hat is linear. These are the vectors. These are the coefficients in front of those vectors. Since it is linear, P hat of this is P hat of this minus P hat of this plus P hat of this. And I can take this constants also out, so I get this. X plus Z times P hat of this one minus Z times P hat of 1, 0, minus 1 plus Y plus X plus Z P hat of 1, 0, 1, 0, 1, 0. Tamam mı? Well, this was defined to be what? This was defined to be 1 minus 1, 0. This was defined to be 1, 0, minus 1. And this was defined to be 0, 0, 0. So this is done. I am just left with this two guys. X plus y here, no, x plus z minus z, so this is just x. X plus z the minus sign. Buradan bir şey gelmiyor. Minus x minus z. Buradan da z. Bu s'in içinde mi? Is it in S? Sum of the coordinate is 0, so it's in S, right? In S. P squared P, I can check that whether P squared is P. So this is P head of x, y, z. P head of x, y, z is this. X minus z, z. So this does what? It takes the first element to itself. So this will be mapped to x. And then when it does, it multiplies this one with -1, this one with -1 and adds them up. Okay. Yani bunu eksiyle çarpacak, bunu eksiyle çarpacak ve toplayacak. -x -1. And the third coordinate is itself. Okay. Well, this is just of x, y, z. So from this, we see that he has composition. He has is just he. Tamam mı? Sen bunu sormuştun değil mi?
Evet, çok güzel oldu ama bir şey yapamam tabii yani. Şurada ikinci satırda şey yaptık yani. P'nin içine aldık x artı z'yi falan. Sonra constant değil x artı z'yi falan nasıl çıkardık? Yani x artı z constant mı?
Bu, if I am given this vector, it's a fixed vector, right? A, B, C are just real numbers. Therefore, x plus z is a constant. Okay? I'm not regarding x, y, z as variables.
Yani x artı z vektör değil zaten.
X plus z is a scalar. I can take always constants out and inside. Okay? Tamam mı? Sorusu olan, inanmıyorum bunlara diyen. İnanmak zorunda değilsiniz. Okay. Okay. Isomorphisms of vector spaces. So, a linear map A hat from P to W is called an isomorphism. Bunu yaptık zaten değil mi? Isomorphism. If A hat has an inverse. Inverse'ü de bir taneydi. W'dan Z'ye. Neydi? Biriyle gidip diğerine dönerseniz identity olacak değil mi? So, a composition, a inverse is what? This is the identity map of W. A head inverse composition, a head. This is the identity map of V. Right? The thing is the following. If you have an isomorphism, then they have the same dimension, at least if they are finite dimensions. Şöyle yazayım. So, fact or onu ne diye yazmış? Ya da şöyle diyeyim. Evet. Okay. Any n-dimensional vector space V over epsilon V is identical. To theta. Why is that? So this is, in some sense, it's nice, right? Any vector space of dimension n is just actually Kn, but it is also disappointing, meaning that, you know, except Kn's, there are no vector spaces, right? They are all the same. I mean, any vector space of dimension n is just Kn. So in that sense, it is a little bit disappointing, but don't worry, there are still, you know, many nice things about vector space and maps. Proof is easy. Well, since V is a n-dimensional vector space, so by the, okay, since dimension of U over the field space of n, V has a basis. Is a basis. Let's say theta P1 up to Pn consisting of n elements. R'nin de bir basisi var. K'nin. Also, beta prime, which is f1 up to fn, where fn is this. So f1 is this, 1, 0, 0, 0, 0. F2 is just 0, 1, 0, 0. And so on up to fn, fn is just 0, 0, 0, 1 is a basis for k to the power n. So there is a, by the proposition we discussed last hour, I have a basis for V, I have a basis for W, which is this vector space. So there is a unique linear map taking this basis elements to these elements. So there is a unique linear map A hat from B into Kn, so that A hat of EI is equal to I from 1 up to n. Değil mi? Bunu yazabilirim. Böyle bir lineer map var. Ama şu da var. This is also a basis, right? For Kn. And this is a set of elements in P. So there is also a linear map taking this basis elements to these elements. So I can just play the game, same game, but this time in the other direction. Since F1, Fn is a basis for W or Kn, there is a linear map, there is a unique linear map. Okay. There's a unique linear map. Let's say we had from K1 to B such that we have of I is equal to I have one of the Bu benim telefonum.
Resim artık kesin hocam.
Yani
Resim artık. Güzel.
telefonlarda zorlar değil.
Ay çok iyi.
Bilmiyorum. Okay. İnsanların onlar için ne düşündüğünü bilsinler. Okay. Any questions so far? So we were given a basis here, beta, E1 up to En, and another basis, let's say beta prime, F1 up to Fn, and then I define a map this way, taking ith element to ith element here, and then B hat in this direction, taking Fi to Ei. Just the opposite digit. Well, composition of these two is also a linear map. So B hat composition, A hat, is a linear map from B into, this goes from B to Kn, this goes from Kn to B. So it goes from this element to this vector space to itself. And what about its action on the basis elements? On the ith basis element, this is just, I'm sorry, it's the effect of A hat of Ei, the effect of what is this? Fi, but the head of Fi is just Fi. So this is identity on every basis element, right? I from one object. There is another map which is identity on every basis element. What's that? B from B to B. A linear map which is identity on all basis elements. Just identity map, right? Identity map itself from B to B sends Ei to Ei because it sends everything to itself. But the thing is this, I have two linear maps, this one, and they agree on basis elements. That these are the same because every linear map is uniquely determined by its action on basis elements. So if this linear map sends the basis elements to the same thing, right, two linear maps, then they are the same. So in composition A is just identity of, similarly, of course, A composition D is identity of Kn, and we are done, right? What we have seen is that I have found two linear maps between these vector spaces, right? And so A hat and B hat, and their compositions are identity maps. Therefore, these are isomorphisms. So we are done. Anlaşıldı mı? So, elements and you have asked isomorphisms. Okay. Direction of vector spaces. Okay, now if B and W are vector spaces over the same field, same, then we define a new vector space, which we will denote like this. B sum W, we will read this as direct sum. The direct sum, of V and W as the set of all pairs. As the set of all pairs V cover W, where V is in V and W is in W. So this thing is just, I'm sorry, so this thing is just the set of all pairs like this. V is in V, W is in W. This is just a set so far. For this to be a vector space, I have to define the operations, vector addition and scalar multiplication, and show that all the properties of a vector space are satisfied for those operations. Okay. Operations. So addition is this. Addition. It will be two vectors or two elements in this set. I define the sum of these vectors as follows. So this is a new sum, actually. It is defined as follows. You just sum the corresponding, components. So first component here is add up with the first component of the second vector, and similarly. So operation is defined component wise. This is the addition operation of the vector space V. This is the addition operation of the vector space W. This is the addition operation of the vector space V plus W, diagram W. So all these three different, additions, three additions are actually different additions. But you know, to simplify things, we don't distinguish them. We write plus for all of them, but you should keep in mind that this is the addition in V, this is the addition in W, this is the addition we just defined in V plus W. What about scalar multiplication? If number is in K and V W is in V plus W, then we define lambda times V W as well. I know how to multiply vectors in V by scalars, and I know how to multiply vectors in W by scalar, so I just multiply them. Okay. I will leave it as an exercise to check that with this operation, this is really a vector space. So you have to check basically three things: that under addition, this set is an additive group, right? Abelian group. We have only defined scalar multiplication, and then there is this distribution laws and multiplication by zero, and so check that the direct sum W is a vector space with these operations. Why do we need something like this, you know, addition of two vector spaces? Actually, usually we will use it the other way around. We will write a big vector space as a sum of smaller pieces. Okay? So that, you know, life is easy. Once the dimension is small, life is easy. For example, the diagonalization we have done last Tuesday is something like that. We divide the vector space into two pieces so that on each piece our linear map acts by multiplying the scalar, right? Yani vektör sayımızı eigen vektörlerin eigen space'lerin direct sum'ı gibi aslında orada yazdık. Öyle ki lineer makinesi uyguladığınızda her bir komponentta ne yaptı? Sadece bir skalarla çarpma olarak. Normalde lineer map çok karmaşık olabilir. Ama vektör uzayını öyle bir parçalıyorum ki her bir parçada map'iniz kolaylaşıyor. So this direct sum will be very useful, but usually we will use it to decompose vector space into smaller pieces, so that on each small piece, linear algebra is simpler. Like on eigenspace, what's an eigenspace? Eigenspace is the I didn't find it is the subspace sent by those eigenvectors. Derseniz bunu neyse onu gelirim. Şurada bir şey var. Proposition. if V and W are finite dimensional, then so is V plus omega, and dimension of this just dimension of V plus dimension of dimension of direct sum is just the sum of the dimension. Okay, and the proof is easy. Since they are finite dimensional, let us just choose some basic. Let beta E1 up to N and beta prime F1 up to Fn be basis for V and W respectively. We claim the following, that claim sorry, beta double prime neutral targeting, beta double prime EI FJ'lerden oluşsun. So the first vector is from the first basis, second vector from the second basis. How many elements do I have? Olmadı. Evet, yanlış çıktı. Basis olan çıktı. O da bir şey basis ama bakın. E1, 0, 0. So En 0 and then 0 F1 0 Fn is a basis for the direct sum W. So that's the claim, okay? Proof is very easy. Let's see the proof. I have to prove two things. First, these elements are linearly independent. Second, any vector in the direct sum can be written as a linear combination of these vectors. Let me start from the first one. So take a second one, take any PW in the direct sum. I have to write this as a combination of these vectors. But this is already in V, right? Since this is in V, V can be written like this. C1 times E1 up to Cn times En for sum C1 up to Cn in K. Similarly, W can be written as D1 times F1 up to Dm times Fn for some D1 up to Dm in K. But then this thing, which is just what? C1 E1, Cn En, and here I have F1, no, D1 F1 up to Dm Fn. Okay. I can write it this way. C1, E1, Cn, En, and then 0 here, and then 0 here, D1, F1, Dm, Fm. And then I can do the following. This is just E1, E1, comma 0, plus E2, E2, comma 0, up to Cn, Pn, comma 0, plus 0, right? P1, 1, 0, D2, F2, 0, Dm, Fm. And the last line will be the following. Okay, so that's equal to, here I can just take this Ci outside. Here I can write this 0 as Ci times C1 times 0 vector. Okay, so there is C1 here and C1 here. I just take C1 outside. Right, so this is just C1 times 0. This is C2 times 0. This is Cn times 0. This is D1 times 0. This is D2 times 0, and so on. So every term here has Ci in it, so I can just take Ci and I have this, and then C2 times E2 times 0. Cn times En times 0. Plus, I have D terms, D1, 0 times F1, D2, 0 times F2, and so on, Dm, 0 times Fm. So any element is written as a linear combination of this n plus m vectors, right? Efendim? Evet. Both vector spaces are over the same base field K. Okay, what about linear independence? We have to show that these are linear independent. So let's see it. Let lambda 1 times E1 comma 0, lambda n times En comma 0 plus lambda ya da bunları da artık mu diyeyim. Mu1 times 0 F1 artı mu m times 0 Fm is equal to 0. Okay. I can take these lambdas inside and then add them up, and we get the following. Lambda 1 times E1 plus lambda 2 times E2 up to lambda n times En, and then I have mu1 times F1, mu2 times F2, mu m times Fm equals, here of course 0 is what? 0, yeah, right, this is the, it should be the pair, and the 0 element of the direct sum consists of the pair 0, 0. So we have this, but this means what? This means that this is 0 and this is 0, but these are basis elements, E1 to En, right? These are base elements. Therefore, this implies that lambda 1 up to lambda n are 0. And again, these are basis elements, so mu1 up to mu m are all 0. So all these coefficients must be 0. Therefore, this is linearly independent. Süre bitti herhalde. Buyurun. Okay.